coupled to the phonon node, exchange phonons, and then the phonon node couples to perhaps a palladium nucleus. And there's different palladium isotopes, but you generate reaction products in the range that George Chambers measured alphas at. So for example, if you take this and go further, if you consider ionization to the ground state, so the nuclei only, you generate something between 19, basically 21 MeV. And if you were to include the fact that some of the final state nuclei would be in excited states, typically you get another MeV, a little bit more out of it. And so that would spread things between 21 and roughly 18 MeV, more or less in agreement with the measurement of Chambers. So this is from my perspective, this is the very first hint that the experiment actually contains information about a mechanism from which you might be able to learn something with a theoretical sample. So conjecture, the implication of the Chambers experiment is that a mechanism exists for energy from reaction at one site to be expressed elsewhere. So this is important conjecture. Now, I've been working with my colleagues in the community to get me some more of these alphas so we could clarify things. And since that time, by now, there are currently roughly five experimental reports that appear to be consistent with this notion. Ed Cecil reported protons near 11 MeV from titanium, which is pretty close to what you'd expect from this reaction mechanism. Lipson and independently Carbu have seen fast alphas out of palladium deuteride and I believe titanium deuteride as well. So this appears not to be a flash in the pan. It appears to be something that can be seen in more than one laboratory. So conclusion is that we've got a new kind of reaction that we can begin thinking about, where a fusion at one site, a nucleus at another site, goes to a fused system at one site and a dissociated thing at another site. So this is a step forward, at least for me, theoretically. Okay, not shift gears. Let's take this notion and go further, because it implies that a different kind of reaction ought to be very much more important. Now, the initial idea was that for the Chambers experiment, two deuterons are going to come together, that perhaps there might be electromagnetic coupling to a nearby nucleus. You can calculate that coupling and find that it's exponentially damped manyfold before you even go a tenth of an angstrom. So the idea is that it can't possibly be electromagnetic coupling, and this notion of phonon exchange became important because a phonon can be extended object. If you've got a highly excited phonon node, then then all you require is that the fusion happen exchange more than one phonon with your excited phonon node. Then your coupling to another system somewhere else ends up being hindered algebraically and can be non-local. The idea is that two deuterons come together at one site as one half of the second order reaction, exchanges phonons with the phonon node. The phonon node has to couple both sites. And then at the second site, phonon exchange results in the dissociation. So the overall second order reaction then conserves energy. One half or the other half of the second order reaction by itself does not conserve energy, but the second order process overall would be conservative. Now, I have modeled this, and I've come up with a couple of conclusions. One conclusion is that in the case of a single highly excited optical phonon node, the coupling can be long range if you have nonlinear interaction with the phonon field. And these formulas, the infinite order Berlin-Wigner, basically you've got your interaction, you have a non-resonant denominator. The moment you're dealing with one optical phonon node, your non-resonant denominator decreases the interaction algebraically. If you had all phonons contributing on equal footing, you would find an destructive interference between all the modes and an exponential decay at the range with a very short distance. Now, the question is if you've argued that you have this site-other site mechanism, the question is what's the dominant process? Which process happens faster than, which second-order process happens faster than all the other second-order processes? Well, in quantum mechanics, we've got a formula for reaction rates, and it cares about the interaction matrix elements squared, and it cares about the density of states. Now, the argument was that if you have a resonant reaction with a bound state, that the density of states could be very high. Namely, if you have chambers like dissociation, ionization reaction, the alpha goes into a continuum. So the density of states is very low because there's a wide range of states. If you had a resonant reaction, the density of states would be very high. By this argument, we could deduce that the resonant version of reaction plus its inverse, where the final state is bound, there's no continuum, and the process is resonant because you have the same thing on one side as you have on the other side. That process should be the fastest process. So the idea is two deuterons fuse at one site, exchange two or more phonons with a very highly excited optical phonon mode. The optical phonon exchanges two or more phonons with a helium-4 somewhere else, dissociates the helium-4, and the overall second-order process is energy conservative, it's resonant, should have the highest possible rate. Of course, as a reaction, it's not the world's best reaction because you don't actually do anything. You have two deuterons helium-4 initially, you have two deuterons helium-4 after the fact. It's almost like they exchanged places or something. So even though theoretically this is supposed to be the dominant process, as a dominant process, it doesn't look very promising initially that you actually would ever be able to prove that this is the dominant process. However, for now we can make conjecture that the dominant other site reaction is the Null reaction within this way of thinking. Detection of Null reaction. Well, can you detect it? If you could detect it, that would be spectacular, because then you could make further progress. Question: is the Null reaction observable? Conclusion. Well, I don't actually believe that you can detect a helium and two deuterons within the submicron region difference under these conditions until that just two of them have exchanged. However, if a helium-4 dissociates through this kind of mechanism, the two deuterons are born close together. You might think, well, the leak, right? Except that there's a Coulomb barrier that they have to tunnel through the lead, and the tunneling probability that's associated with the Coulomb barrier is very small. So the thing is if you actually do this, when the helium-4 dissociates, the two deuterons that are born, they're made from the dissociation, they're born close together, and they're escaping from one another is hindered by the Coulomb potential. Consequently, it seems maybe there's a break here such that we can do it. So the idea then is that if you come in with a projectile, and if the two deuterons having been created through phonon-induced second-order dissociation of the helium-4, if they happen to be close to one another, maybe you can hit them. And if you can hit them, you get a reaction. Because if the two deuterons come together, they'll make the helium-4, you'll have 24 MeV. 24 MeV on the nuclear scale is like a firecracker or something. It blows up, it makes things happen. And in principle, you ought to be able to see that. Theorem. The deuteron pair formed from resonant dissociation has a low probability of tunneling apart. Something could be proven, can be proven, has been proven from conventional accepted quantum mechanics.